So I want to finish off the slides that I have on Docker. We're going to come back to Docker again, though, because one thing we haven't looked at is how do we actually create our own Docker images, which is a pretty important part uh, of the tool. But I'm going to park Docker and move on to another topic, but it's directly linked to containerization, and this is the topic called Kubernetes. We'll spend about a number of weeks, really, maybe 3 weeks-ish on Kubernetes, and then we'll go back to Docker again. There's a lab for this week, which is this one here, which is dealing with the stuff that we looked at last week, actually, this whole area of networks within the Docker environment. So the labs are slightly out of sync with the lectures, but so be it. What I want to talk about briefly to wrap up Docker today is the area of volumes. Now, you actually looked if you worked your way through the second lab, there was a section on it. I probably should have told you last week to hold off on it, but the section at the end of last week's lab was on the topic of volumes. So really, what I'm going to cover today um, is linked directly to this here. So again, as I said, the lectures are slightly out of sync with the labs, but things catch up eventually. Do I have any questions from people on the labs? I'm not getting a whole lot of questions from you over Slack, which I'd assume means everything is going fine. Does anybody have any questions about the labs so far? No? Okay. There was an exercise actually in the first lab, which I should have really given you a solution to, and I will do that later on today or early tomorrow. Okay. I'm not sure if there's an exercise in the networking lab, but see how you get on anyway. Right, back to these slides here and just I want to finish them off. But as I said, the topic is familiar to you now if you have worked your way through all the labs so far, which is this area of volumes. And volumes essentially allows us to attach a part of the host file system to your containers file system. And there are obvious reasons why that is desirable. But technically, what a volume is as what I just said there, it maps a part of the host file system to the containers file system. And really, the reason we need to do that, really, as much as it's a nice feature, is when if a container creates data during its runtime, once that container shuts down and is deleted, all of that data is lost because it's internal to the container. So if we want to persist any data that the container creates during runtime, and the classic example would be when your container is running a database server, and that's exactly what you would have done in last week's lab if you worked your way through all of it. Um, when a database container shuts down, clearly we'd like to persist the data so that when we start it up, the container again, it can still access all the data created in the previous execution. So that's the simple and obvious use case. As well, maybe a container might create other types of data, not necessarily database related stuff that we'd like to persist. We know at this stage how to link a part of the host file system to um, to the containers file system using this -v option, where you just specify the path name here of the host can be either in relative or absolute terms, and the path name of the container is always in absolute terms, the absolute path name. And now, again, this is probably the third time I've said it. What this slide is telling us, you actually know from last week's lab. Again, if you've worked your way through it, there are two types of volumes in Docker world. The original type was called bind mounts, and then more recently, Docker added something called name volumes. The image here is something that I just grabbed off the internet, and it's trying to illustrate the core difference between bind mounts and named volumes. And what it's trying to get across is, so okay, the big white box is our host, and this kind of gray box here is the host file system. Now, when you start up the Docker engine, the Docker engine clearly it creates um, it creates its own kind of set of files and folders that are private to it. So that's represented by this kind of box here. So all of the files and folders in here are owned by the Docker engine. Yeah. Now, okay, I've got a container running within my Docker environment, and if I create a bind mount between this container and uh, the host file system, the kind of the connection is between the container and some part of the file system itself, the host file system. So this is kind of a link to the gray box, to the host file system. Whereas if I create the second type of volume, which is called a name volume, name volumes are actually physically they're within the Docker's uh, they're within Docker's part of the host file system. Okay, and so that's why the link here, which is representing named volumes, named should really be up here. The link is to this part of the file system, if you like. We cannot access this part of the file system using, Windows Explorer or Finder, Windows Explorer if you're working on a Mac, Finder, or sorry, if you're working Windows, Finder if you're working on a Mac. Windows Explorer allows us to navigate around this part of the host file system, but we can't really get at this part. So that's kind of the core difference between a bind mount and a name volume. Bind mounts are actually visible within the file system. We can actually see the part of the file system, whereas name volumes are internal to Docker, and we can't access them from any kind of host-based application like Windows Explorer. It has some part of, sorry. This is just representing some part of RAM that Docker owns. But just to drill in a little bit deeper, so bind mounts first. Anything new here? When you create a bind mount mapping, if the host path that you're specifying doesn't exist, then Docker will actually create it. So a bind mount now is, if I go back again, where you're pointing some part of the host file system that you can access the user. You're linking that with the containers, some part of the containers path, internal path. But anyway, so with a bind mount, it actually will create the host file and folders if they don't already exist. And like the advantage is that we can actually physically navigate around that part of the host file system. And so essentially the we can see some of the files and folders that the container is using. We can see them without having to go Docker exec, without having to create a tunnel into the container itself. We can actually see a particular part of the Docker's file system after creating a bind mount. So that's kind of advantage. It's also a disadvantage because that really means, like one of the points we made about containerization is that each container is isolated from its environment. But with a bind mount, we can now actually see some part of the container's internal file system because it's linked to the host file system. So I'm saying down here at the end that really bind mounts, they break the kind of isolation principle. Some people think that's disadvantage or a weakness of bind mounts. Anything else here? Yeah, like when you specify the host path name, clearly the file system on a Mac is different from the shape of the file system on a Windows machine. So, if I'm working on a Mac here, if I give you a command with a bind mount as part of the Docker command, then, I'm giving you part of a Mac's file system path name. That's not going to work in Windows. That's really what we're kind of getting at here, that they rely on the host file system having a particular structure. It's a fairly small disadvantage, but it is a disadvantage. Uh, and like within Docker, you can't manage. Docker cannot manage the host file system, so you have no control over it from Docker's perspective. You can manage it from the host itself, but you can't manage it through Docker if you like. And so yeah, we've seen this kind of stuff before. So there's nothing new there. Creates the source of the host path name if it doesn't exist. That's fine. Target path name, that's okay as well. Oh yeah, you can also specify the access mode as part of this entire kind of string here. Okay, there are really only two access modes: read write and read only. It defaults to read write. So the colon RO there is saying that the container has read only access to this part of the host file system. Okay, that may be desirable. Uh, there is another syntax for specifying these bind mounts. It's a much more kind of long-winded syntax. You'd very rarely see it used, but this is the syntax here. So there's the mount option on the Docker run command, and you're specifying what type of bind mount, what type of mount is it? It's a bind mount. These are all kind of comma separated. The source path name, the target path name, and the access mode as well here at the end. So it's more long-winded really. And as I said, I don't think people use it much anymore. They use the more shorthand form up here. Uh, oh yeah, one advantage of this using this syntax is that if the source path does not exist, like up here, I'm saying if the source path, the host path, if it doesn't exist, uh, Docker will automatically create it. Whereas when you're using this approach, Docker is actually going to throw an exception if the host path doesn't exist. So it might be desirable to have that actually when you're running a particular container. You don't want Docker creating new paths on the host file system. You just want it to inform you that, look, the host path doesn't exist. You have to create it manually yourself first. That may be desirable. Other than that, it's pretty straightforward. I don't think there are uh, anything unfamiliar to you in all of this so far. Moving on to name volumes. Everything in name volume is kind of bind mount isn't, and kind of vice versa. So named volumes are that's where the source, if you like, the source. Oh, sorry, I shouldn't really say that. No, no, forget about that. Let's just read the bullet point maybe. So the name volumes, they live inside Docker. They're not actually part of the. They're not part of the host file system that's accessible outside of Docker. Right. Um, uh, yeah, they're not visible on the host file system. If you're using Windows Explorer, you can't see them. Advantages then, like the advantages are what were the disadvantages with the bind mounts. Yeah. They can be managed by Docker, so there are Docker commands to manage these named volumes. Uh, they are more performant. Okay, so you get a quicker kind of response time as you're application is trying to access the data within a name volume, the speed of access is greater than trying to access data from a bind mount. So that's obviously a good point. Uh, Another thing is with named volumes, you can link it. You can specify a driver when you're creating a name volume, and that driver option allows you to associate a name volume with some cloud storage. Okay. By default, a name volume is considered to be local to the Docker installation, but you can link it to, let's say, um, Elastic Block storage on the AWS platform, for example. So that's clearly a nice aspect of name volume. We won't necessarily use that, but it's there anyway. The command looks, oh yeah, sorry. These are just some of the commands, and you've probably played with them actually in last week's lab. So with a name volume, as I said, it's all managed by Docker. So you can get this is how you create a name volume. Now, there are many options here that I'm not specifying. One of the options would be what driver am I linking to this name volume? It defaults to local, which means the name volume is just stored within the Docker installation on your local machine. And there are other options as well, like the size of the volume, the access mode, etc., etc. So we're assuming all the defaults here. If you don't give it a name, you don't have to give it a name, but if you don't give the volume a name, then Docker will generate uh, it'll generate a kind of hash value which represents the name. Now, just in have I started up my Docker? Oh yeah. Uh, just in terms of the GUI, you know, you can see over here, there's a section on volumes. Now, when you click on this, now, okay, I have only one volume, but I'm pretty sure you are going to have a number of volumes already created, and you might be wondering, well, where did all these other volumes come from? Turns out that for many containers, for many images that, sorry, for many containers that you have played around with so far, by default, kind of Docker creates a volume for each of those containers. So you'd see a whole list of them here, and their names would be just hash values. But you can actually get rid of all of those. Um, Docker volume ls, that's okay to list all the volumes currently on your local machine. Docker volume inspect, if I just do that on the one that I have. So I've got a volume called, let's go back here, uh, called my TMDB. So if I go, you can see here one of the properties is driver, and it's set to local, which means, as I said, the volume is actually uh, local to this machine. Anything else of interest when it was created? Labels we don't care about. Like you can see here now that this is the actual path name of physically where the data will be stored. Right. Now, if you remember, I was telling you that there's something kind of happening behind the scenes with Docker Desktop. When you install the Docker Desktop, which is really just an application, when you install that application on your local machine, what's actually happening is you are installing a hypervisor. The hypervisor technology is called HyperKit. On top of that hypervisor, there is a Linux virtual machine being spun up. and then the Docker engine is installed on that Linux virtual machine. Now, this path here is a path within that Linux VM. Okay, um, we can't actually get at we cannot get at the Linux virtual machine that's being run internally by Docker, uh, but well, if we really tried really hard, maybe we could, but you're not really meant to go poking around that Linux VM. So anyway, that's where that path name comes from. It's actually a path within the Linux VM that is running on your machine. And then what else? Okay, there's anything else of interest there, I think. Back to the slides. Uh, to remove a volume, obviously it won't allow you to remove a volume if it's currently being used by a running container. So you'd have to detach the container first, and it will tell you that anyway. This is kind of a useful command. This command will delete any volumes that are currently not linked to any container. Although I suppose you'd have to be careful about that, but certainly that command, this prune command, is useful to get rid of all of the volumes that were kind of automatically created by Docker when you were running some of the other containers like Nginx and the Apache web server and all of those, because presumably you don't really want those volumes. That's okay. So really the only difference here, like you use the -v option again, the only difference here is that the thing here won't be a path name. It'll just be the name of a volume. You can use the --mount option as well for mapping a named volume to a container path. But again, the -v option is much more shorter to write. And I think that's about it, really. Um, Now, as I said, I'm going to park Docker now for a couple of weeks, and then we'll come back to it again. I'll just stop for a second in case there are any questions so far. No? So our next topic is Kubernetes. And if you've read anything about Kubernetes, you'll know that Kubernetes, that title is wrong there, sorry. That should be Kubernetes. That's a mistake, and this is also wrong. Uh, the image is right. Sorry about that. So at least I've got it right here anyway. So we're going to have a set of slides, which I'll only just start into really today. And then for the next couple of weeks, all of the labs will be around Kubernetes. And the first assignment as well uh, will be concerned with this Kubernetes platform. So I need to escape out of this. Kubernetes, or for short, it's written as K8S, 8 because there are 8 letters in the word Kubernetes. And as I say, if you read anything about Kubernetes, you probably know that already. So there are no prizes for getting that right. Let me just bring up my pen. So what Kubernetes was developed by Google, and initially they developed it as an in-house solution to a problem that they had. And the problem that they had was they had loads and loads of applications, containerized applications, running on VMs, and it just became unmanageable. So they needed some software to help them to manage the lots and lots of containers that were running uh, in-house, so to speak. And they came up with this solution. I think it was called Borg initially. This is back around is it 2014, the slide is saying there. And they then, fortunately for us, they actually handed over, they open sourced this Borg uh, tool, which and renamed it to Kubernetes. And they open sourced it, and an organization called the CNCF, the Cloud Native Computing Foundation, which is again, is a body that manages or looks after lots of open source software that's related to containerization. Um, it's a bit like the ECMA organization, the European Computer Manufacturers Organization. Uh, the CNCF has a similar kind of role, but specifically for, okay, what are called cloud native applications, which is inextricably linked to the whole kind of Kubernetes and any tooling around Kubernetes. So I'm saying up here, it's an open source system for automating the deployment, scaling, and management of containerized applications. Like we've been running containers on our laptops, but presumably at some stage we'd like to deploy our containerized applications so that uh, it can be globally accessed by our user base. Yeah. And so, I mean, one way we could do that is if we wanted to use, let's say, the AWS cloud provider, we could spin up an EC2 instance on the AWS platform, SSH into that instance, install the Docker, because the EC2 instance will be a Linux VM, or we can configure it to be a Linux VM. We could manually install the Docker runtime on that VM, which is a very easy thing to do. And voila, we've got a cloud-based Docker environment created, and we could deploy containers into uh, that container engine running on a VM in the cloud, and make it accessible to uh, maybe put a load balancer in front of it, or make it accessible to the our customer base globally if we wanted to. So that would work fine. But we do have to kind of take care of creating that environment. And as well, we'd have to take care of monitoring to make sure everything is working okay. And if certain containers crash, we have to start them up again. Um, or if there's a high volume of demand on our containers, on certain containers, how do we deal with that? This is this area of scalability. So it becomes, and that's really the problem that Google had, and that's why Google came up with their in-house solution, which is now this Kubernetes solution, and it is used all over the industry today. That's fine, and explaining what the meaning of the word Kubernetes is there. So, what problem does this Kubernetes platform, what problems does it provide a solution to? And I've kind of listed maybe, I think, five, but there are probably other problems that it's an ideal solution to. And so the first problem, I've probably kind of mentioned these in passing. Um, so an application is comprised of multiple uh, containers, and we saw that a very simple illustration of that in last week's labs, where we had two containers making up our overall application. Now, these containers are going to be running on a cluster of nodes. A node is essentially a VM. It could be a physical server, but more typically, it's a virtual machine. The virtual machine might be running on our own hardware, on-premise hardware. It might be running in the cloud, like on an EC2 instance. Um, but we've got a cluster of them. So we've got many VMs, all of which are running containers. Yeah. And if a container, what am I saying here? If a container or if a container or an entire node, one VM, if it crashes, uh, what are we going to do? We need to get those containers up and running again. If an entire node or an entire VM crashes, we need to start up the containers that were running on that node, start them up on another node that's part of the cluster. Um, so do we have to do that all manually? Well, Kubernetes actually takes care of it automatically. Kubernetes will monitor the various containers that are running on the cluster of VMs, cluster of nodes. It will monitor them and it will be notified if a container crashes and it will try and restart it automatically, which is what is referred to as self-healing. So number one, it's tracking to make sure all the containers that are running across the cluster of nodes, that they're all running successfully. If any one of them goes down, it will automatically restart it, which is what's referred to as self-healing. And does the same for a node. If an entire VM crashes, um, Kubernetes will be notified of that and it will try and either spin up a new VM and start all of the containers that were running on the crashed VM because it will have a record of what containers were running on what nodes. It, it, uh, it has a sort of a database of all of that information. So it will either spin up a new VM or try and restart the one that has crashed and essentially get the whole environment back to the state that it was in before either a container crashed or an entire node crashed. And that happens automatically. Okay, that is built into Kubernetes. So that's clearly a significant advantage of this Kubernetes platform. Problem number two, we're saying here that a container Uh, oh yeah, container experiences a spike in traffic. So there's just, for whatever reason, there is a large volume of traffic targeting a particular container, uh, you know, user base. A large volume of users are currently using a particular application. So the container or containers that are dealing with those user requests are going to experience performance degradation, and from the user's perspective, they'll experience latency, slowness in response to their requests. The solution to that clearly is to scale up uh, the number of instances of the containers that are experiencing the spike in traffic. Scale up really simply means create multiple copies of the container. Um, uh, But again, Kubernetes will take care of that. It performs auto scaling. You can have a certain amount of control over the scaling policy, as it's referred to. But once you define the scaling policy might say if there's an X percentage increase in traffic, then create, two more instances of the container or something to that effect. So once you define the policy, then Kubernetes will take care of enforcing that policy by scaling up, making multiple instances of a container, and similarly scaling down if uh, the spike in demand suddenly starts to decrease, then we don't need to have additional instances of our containers running. So it will start shutting down containers. And once it starts spinning up multiple instances of a particular container, then it will also obviously take care of load balancing the traffic across the various instances. And again, that's all built into the Kubernetes um, software. Problem three, presumably you want to upgrade your applications at some stage. add new features or fix bugs, whatever the nature of it is. And once you uh, test your changes, then you want them to be applied to the containers that are impacted by that. Well, again, Kubernetes will do that for you. It'll actually perform what are called rolling deployments. Rolling deployments. So if let's say we've got a container that is running a particular image and we've added a new feature to that that image. But at the moment, let's say there are 5 containers running that image, 5 copies of a container running that image, and those 5 copies would be distributed, let's say, globally. Um, uh, how do we actually apply the updates to the containers? Well, rather than shutting down all 5 containers and restarting them with a new image, that would really mean that that particular application is not going to be available to your user base as the shutdown and restarts are happening. So what Kubernetes will do is perform what's called a rolling deployment. It will apply the changes to the containers one by one. Uh, Also supports Canary. Okay, Canary deployment is maybe you don't want to apply the changes to all of the copies of a container. You just want to apply it to one and just see how it's getting on in production. And if there are issues with it, well, at least some of the containers are still running the old version. A small number are running the new version. And so you're not impacting your user base as much as if you had done a complete deployment. So Canary deployment kind of uh, as I said, applies the changes to a small subset of your containers, monitors to make sure that there are no issues. And if there aren't any issues, then it will continue on rolling out the upgrade to the other containers. Uh, Problem number 4, uh, okay, you want to upgrade an entire application. By an entire application, that might mean there are a number of containers now that make up our application, and we want to roll out changes across all of those containers. Again, and if there are any issues after we roll out the changes, if there are any issues, then we'd like to roll back to the previous version of the application. Again, that can be very tricky if there are a large number of containers involved in the upgrade. But fortunately, Kubernetes will take care of the rollout and the rollback if necessary. And it will know that it should roll back because once it's rolled out the new changes, it will monitor to make sure that there are no containers crashing as a result. Um, so it knows when to roll back. Last problem, and there are others. Yeah, you've got a container running a particular image, and you want to change the configuration of that image, but you don't want to shut down the container. Because again, shutting down containers means, it can impact on your user base. So you want to reconfigure a container without shutting it down. And there are techniques called um, configuration maps that effectively allow you to reconfigure a current running container without actually having to shut it down. So lots of really nice features available to us in Kubernetes that otherwise we would have to do it manually or try and script it ourselves, essentially, right? And then obviously maintain that scripting code. Okay, so let's dig into the little bit more detail about Kubernetes. So I'm saying here you install Kubernetes over a set of nodes or a set of VMs. So it's kind of, if you can visualize, you've got a number of VMs that make up, I've got a VM here and I've got another VM here. And another one here. Drawing, sorry. One here. Well, you sort of install Kubernetes across on top of those, right? Um, that's a bad drawing, but anyway. Now, and we refer to each of these VMs as a node. Some of the nodes you classify as worker nodes, which I'm saying over here. Worker nodes are where you actually deploy containers onto. The set of worker nodes that make up your Kubernetes installation, some people refer to it as the data plane. Right. The, a subset of the nodes are called master nodes, and clearly, the master nodes are responsible for kind of managing the worker nodes. Uh, and the master nodes are referred to as the control plane, and that's a word, or that's a phrase that we come across a lot when we talk about Kubernetes control plane. Well, the control plane is the set of master nodes. Um, the visual here, is illustrating this. So you're clearly going to have, in most cases anyway, you're going to have multiple worker nodes. Now, you're also advised to have more than one master node, because clearly if the master node crashes for whatever reason, then your whole Kubernetes installation is unavailable to your user base. So you will have a number of nodes will actually make up will make up the control plane. One of the masters will be the primary one. The other ones will be backups. Your typical kind of scenario. And if the primary master node goes down, then one of the backup masters steps in and takes over the role of essentially managing the cluster of nodes. Um, yeah, so we have more than one master for fault tolerance, or and also for availability. The set of nodes is referred to, the set of workers plus masters is referred to as a cluster. So we talk about a Kubernetes cluster always. And what I'm trying to get at over here is that containers are only deployed onto the worker nodes. You don't deploy containers on the master nodes. Now, if we want to look at the internals of these two types of nodes and Kubernetes, some of the Kubernetes components are running on the master node, and you've got other Kubernetes components running on the worker nodes. Okay, so it's a typical kind of distributed installation. So as a user, let's say you want to deploy a container onto one of the worker nodes. Well, what you interact with is the API server part of Kubernetes. So the API server is your main entry point as a user. Okay, and you may as a beginner anyway, it's a CLI. It'll be a CLI, command line interface tool. That's what you will use to communicate with the API server. So you might have a command that says, I want to deploy a particular image onto my Kubernetes cluster, and whatever the command is to do that, and we'll do lots of it later on. That command is received by the API server. So let's supposing that is the command that the user has issued from the CLI. I want to deploy a particular image to to the cluster. You don't tend to specify what node you want to deploy to. You just say, I want to deploy a particular image to the cluster. The API server will communicate with the scheduler. The scheduler is responsible for deciding which of the worker nodes should the container be spun up on. And it will do that based on what kind of resource requirements does the container have, i.e. CPU, RAM, um, network bandwidth, and the scheduler will know what is the current status of the various worker nodes in terms of how many containers are currently running on the various nodes, how much CPU capacity is available on the various nodes, how much RAM capacity is available on the worker nodes. And it gets all of that information from this component over here, the etcd. Etcd is essentially a database, right? And it's a database that contains information on the current state of your cluster. By state, we mean what what is installed, what containers are running on what nodes. Okay, and lots of other information as well. Which of the worker nodes are currently running? What is the remaining capacity, CPU and RAM capacity that's available on the various worker nodes, et cetera, et cetera. So the etcd is the database of the current state of the cluster. So the scheduler will check with the etcd to find out where should I schedule this container that the user has asked me to start running? Which of the nodes should I schedule it on? And it'll make that decision, and then it will ask the Kubernetes controller to initiate the starting up of a container on a particular node. The controller communicates with the uh, kubelet component. So the kubelet component is only running on worker nodes. It will communicate with the kubelet component of the node that has been selected by the scheduler. And the kubelet component will talk to the Docker installation to start up a new container for with a particular image. I'll talk about the word pod here in a second. So here's my container, let's say. So kubelet runs on each worker node, and it's really responsible for communicating with the API server. I probably should have said, actually, it's not the controller that talks to kubelet. The controller will ask the API server to tell kubelet to kick off a new container uh, on its node. Yeah. If a container crashes, then kubelet tells the API server that uh, a container has crashed. API server will update the database. The scheduler will come along and decide uh, should it move the container to a different node, or what should it do? Should it try and request the restarting of the container? All of that kind of stuff. Proxy is the only remaining component. Proxy is responsible for handling all kind of network related stuff in your Docker installation on a particular worker node. And Proxy also is the component that receives requests, you know, ordinary user requests. This is sort of your developer over here. This is your user base that are trying to use your applications. Okay, so all the requests to maybe send a HTTP request to a particular container. That's all managed by the proxy. So API server, scheduler, etcd, uh, controller, kubelet component, proxy. They are the main um, modules that make up the Kubernetes installation. And clearly, you have a Docker runtime as well. Or sorry, you've got a container runtime running on the worker nodes, which in our case would be Docker, although it doesn't have to be Docker. Okay. Now, um, let's go back here actually. We don't talk about containers in Kubernetes world. We talk about pods. So anytime you hear the word pod, you can effectively, in your own mind, replace that with container. But so a pod is just a wrapper. Okay, it's an abstraction of a container. So Kubernetes is all about pods, running pods. So what's a pod? A pod is the smallest unit of deployment. So we deploy a pod to a worker node, strictly speaking, even though for this module, and in case and more generally, a pod is just a single container. It has a single container within it. Okay. Um, but in general, a pod could have more than one container in it. That's kind of the point, really. That's why the Google people don't talk about containers, they talk about pods. Okay. So it's the smallest unit of deployment, or the smallest unit of deployment is a pod. It encapsulates a group of containers. So technically, there can be more than one container in a pod. Okay. The containers within a pod, they share the same local host network. That's fine. And they share the same storage. Uh, so any volumes within the pod anyway are shared by all containers. The difference between the containers, or like our visual here, like we've got two containers running inside this pod. Uh, Typically, one container would be listing on one port, the other container would be listing on another port. Now, before you start thinking, okay, maybe a typical example of this would be this might be a web API container and this might be a database container. That is not the use case for having multiple containers within a pod. You should never do that, right? For that case, where you have a web API and a database, you'd run the web API in one pod, you run your MongoDB database, for example, in a different pod. You never put those two together. There is a particular use case for the, uh, the second. You'd very, very rarely have three containers in a pod. The most would typically be two, but there are particular use cases as for the second container in a pod. The main container would be, you know, whatever the main application is, a web API, a database server, a web server, or whatever. Where the word pod comes from is kind of being illustrated here. Pods occur in nature. Some vegetables kind of grow in pods. Typical of the classic example would be peas. Peas that we eat, they grow in pods. Okay, so that's where I guess the Kubernetes people, or sorry, the Google people, got the word pod from. Well, I'm not guessing it. It's actually where they got it from. A pod is assigned its own IP address. Bring us back to the world of Docker, just like a container. Up to now had an IP address when we were running containers on our Docker desktop environment. In Kubernetes world, an IP address is assigned to a pod. Uh, okay. Uh, but that IP address is only visible within the cluster. You cannot access the IP address of a pod from outside the cluster. And just like the IP addresses that are assigned to containers in our Docker desktop environment, the IP address that's assigned to a pod is also dynamic. So if for whatever reason a pod crashes and it has to be restarted, then it will get a new IP address. Uh, where the kind of use case for having multiple containers, and as I said, even though in theory you could have three, four, five containers within a pod, in the vast majority of cases, it will only be one container. But in some cases, it would probably never get up to more than two containers in a pod. The second container is often referred to as the sidecar container. Okay, like our image over here with the sidecar for the motorcycle. And like an example of so you'd have your main container, which is your, we could call it your application or your app container, and then we have the sidecar container. Maybe the role of the sidecar container is to record all of the traffic, all of the requests that are being made to your main application container. And maybe this guy writes a log of all of the requests to some external volume. Yeah. So it's essentially kind of a monitoring, it has a monitoring role. Yeah. Or another use case, which is kind of what this image is showing, is another use case might be that the sidecar container, they share a common volume within the pod. And we'll see how to set this up. But maybe the role of this container is to retrieve configuration information for the main container. So let's say this is well, okay, I have GitHub here, but it could be any cloud, uh, cloud source, data source, right? So we could push a change to a GitHub repo. Maybe that change triggers is there's a webhook maybe between GitHub and this sidecar container, which means that the sidecar container now is aware of the fact that a change has been made to the GitHub repo. But maybe this GitHub repo just contains configuration information for this pod. So the sidecar container would pull the data from the GitHub repo and write it to the volume, and that volume is used by the main container for configuration purposes. So we're kind of dynamically reconfiguring our application container, and the sidecar is taking care of providing the up-to-date, providing the updated configuration data. But that's another use case for it, right? So it has just a side role, hence its name, kind of sidecar container. We'll never see this, unfortunately, in this module, but just to make you aware of when might you have more than one container in a pod. The containers in a pod share the same network. We've kind of already said that. And oh yeah, they have different ports. I've made that point as well. Um, when you delete a pod, and you don't delete containers in Kubernetes world, you delete pods. When you delete a pod, clearly you're deleting all of the containers within that pod. We don't scale up containers, we scale up pods, and scale down pods. So scaling is at a pod level rather than a container level. Um, That's okay. And I've kind of already made this point that an IP address is assigned to a pod, but that IP address is private, which means it's only visible within the cluster, and it's dynamic. Now, um, fortunately, now we actually have a Kubernetes cluster available to us, and you'll be glad to know you are the first set of students in Setu that have a Kubernetes cluster available to us. You may have heard of the Walton Institute. The Walton Institute is a research um, group within Setu, and they only last June actually they made a Kubernetes cluster. They manage kind of a Kubernetes cluster and have made it available to Setu students and staff. And so that's what we will be using for the rest of this uh, section of the module. Now, I've asked the Walton people to create accounts for you, and they did that. But when I started just playing with the accounts there last week, there were one or two issues with them. So, what I'm hoping is that by tomorrow's lab, those accounts will be ready for you to use. And I will send a Slack message to each one of you individually, telling you what your Kubernetes cluster username is and your password is, so that you can then log into the cluster. And so I've got an account on this Kubernetes cluster. And if I switch over, we will interact with the cluster from the command line. Uh, the Kubernetes installation is a Red Hat installation. Red Hat have a software platform called OpenShift, and the full name for it is the OpenShift Container Platform, or OCP. So that's the particular kind of variation of Kubernetes that we'll be using, but it is a fully fledged, it's an enterprise kind of standard Kubernetes installation. And so what you will do, in fact, if I just maybe, if I go into this week's lab, so if I go back to Docker, and here's this week's lab. The Secret Lab is all about Docker networking, but at the very end here, there's a section called OCP Kubernetes. And if I go into that, what this steps you through is the kind of setup that you need to go through. There's very little in it, really. Essentially, all you need to do is log on to the Kubernetes cluster dashboard and download the CLI, command line interface tool that we will be using. The tool is called OC for short. And once you've downloaded the OC tool, the OpenShift container tool, CLI tool, then you will be able to use it from your command line. And so I've done that already. And if I go, let's say OC version, okay, so we're running Kubernetes version that. Sorry, that's the, no, this is the version of Kubernetes 132. I think the most up-to-date version is 1.33. This is the version of the API server. That doesn't really mean anything to us. This is the version of the Kubernetes, the OC client. Okay, that's all fine. If I just do OC get nodes, the cluster, it looks like the cluster is made up of how many? There's three master nodes. So there's the kind of the primary master nodes and two backups. That's actually what's recommended by the Red Hat people. And we have got three worker nodes, worker 0, worker 1, worker 2. Yeah. And if I just go, in my case, OC get pods, I don't have any pods running. That's fine. Wash. Uh, I have, I didn't realize actually I'm gone over time. I don't know if you're still there or not. I better stop straight away actually, and I'll touch base with you tomorrow morning. Completely lost the track of time.